Now we are going to address a very important question from the point of view of the auctioneer, how to maximize the revenue. So far we have only discussed about the truthfulness, but now we not only want to reveal the information truthfully, but we also want to maximize the payment that has been made by all these agents. Now, when we are talking about the revenue optimality, and that is what we mean by optimal auctions, we have to assume some sort of a prior over the types or the valuations of the agents. And why is that? If we try to do a non-prior, try to maximize the revenue from a non-prior setting, we'll have to consider something like a worst case revenue, and the worst case revenue might not be that good. It can be very less compared to what is possible to earn in practice. And the reason being that when you are selling an object, when the auctioneer is selling an object, it might also have some information about the valuations of the buyers from their previous interactions. If there is an object which is being sold over time, or similar kind of objects being sold in an auction over time, then it has some sort of a prior that what the valuation distribution is, and accordingly we can define the expected revenue that you can earn from this mechanism. And that is the reason we will now shift to the Bayesian setting, and we will redefine these notions of incentive compatibility and individual rationality in the Bayesian setting. So Bayesian incentive compatibility we have already discussed very early in this mechanism design segment. So it says that so now we are going to define BIC in the context of single object allocation. Now assuming that the type set are intervals between 0 and BI for agent I, and the common prior is defined on top of that type profile. So it's a Cartesian product over all the types of all these agents. And let us assume that this lowercase g denotes the density of that common prior distribution, which is a CDF. Now, with this notation g minus I, s minus I given si, we are going to denote the conditional distribution over s minus I, the types of the type vector of the all other agents, given agent i's type, which is si. So what we are assuming that agent I knows its own type. This is something like an interim state where it knows its own type, but it does not know the types of the others. It only can predict or have a belief over that, which is probabilistic. Similarly, lowercase g minus I is just the density. And all these things, s minus I given si, this is derived from the original g using the Bayes rule as before. Now what we are going to say is that every mechanism, so the mechanism is again mapping on the type profile into an allocation, which could be a probabilistic allocation, and this payments, the actual payments that has been made after the realization of the types, this induces an expected allocation. So when the agent I does not know the types of the other players, it can only predict what will be the allocation in an expected way, and we'll define that shortly. So it can define the expected allocation and the expected payment according to those common prior, capital G, and its density lowercase g. And those payment, this expected allocation and expected payment rule, we are going to define by this alpha and pi, the vector pi. So what is this alpha? So alpha again has components for each of these players. So this is the ith component of that allocation. But now notice that it is no longer a function of s minus I, because we are going to take the expectation with respect to s minus I, and therefore it is only function of two things: what its true type is, and what is its reported type is. So now it is going to be defined in the following way. So look at this part, which was there in the previous setup also when we were talking about this randomized allocation, but the randomized allocation was in the prior free setting. So it was defined for the entire type profile when SI, so agent I sees its type, which is SI, and the type of the other players is S minus I. This was the probability of allocation of that agent, of that object to that agent. Now, on top of that, what we are going to do, because agent I does not deterministically know what S minus I is, it is expecting that with respect to that belief, which is S minus I given Ti. So Ti is its true type. So the belief will depend only on the true type, while it might report something different. So based on its report, the mechanism will work, but it will always evaluate that mechanism according to its true type, and that is why there is this difference. So notice that this one is the same one which it has reported, and this type is the same one that is its true type. And at this point, we are also, I would like to make one comment that we have seen deterministic mechanisms where the allocation is exactly giving the object deterministically to one agent or to some other agent. We have seen in the previous setup in the module on Meyerson's mechanism that you can also give randomized allocations. Now that is after everybody has reported. So this randomization is happening on the side of the mechanism designer. So mechanism designer may toss a coin or do some randomization and give the object probabilistically to one of these agents. So this is one level of randomization that happens at the mechanism designer level. But the probability or the prior based thing, so this randomization is actually happening at the agent's place. So the agent is creating its belief or has a belief based on their G minus I, the common prior, and it is taking the expectation with respect to that belief. So that is another randomization, how this S minus I's are getting generated in agent I's own mind, and we are taking the product of these two different probabilities and then taking the expectation over this S minus I's. So this is what I wanted to keep in mind, because whenever we are talking about the single object allocation, particularly when we are talking about Bayesian incentive compatibility or some guarantees in the Bayesian world, and also our mechanism is also randomized, then we have these two levels of expectation. And the first expectation is coming from the agent's side, which is the belief over the types of the other players. And the second level of randomization is coming from the mechanism designer side, how it is allocating the object to the different players. So something to keep in mind. So similarly, we can define what is the expected payment for this player I. Again, SI is the reported type and TI is the true type. And as before, we are going to take the expectation with respect to this posterior distribution. So you can call this a posterior, given its own type. It is taking the generating the belief over the types of the other agents, taking the expectation with respect to the actual payment, which is given by the mechanism. Because it is reporting SI, the mechanism will decide the payment according to that. And assuming that the other players are reporting S minus I in truthful manner, so here the probability can only be defined in terms of the true valuation profile, not what they do if they misreport. So if that happens, then this is the expected payment for player I. And therefore the expected utility will be just that so when agent I is reporting his type truthfully, let's say, so SI is actually equal to TI. In that setting, you can write it as TI multiplied by that expected probability of this allocation minus the expected payment. So this is sort of the interim utility that this agent I is getting. Now we are in the right position to define what is Bayesian incentive compatibility. As before, the inequality that when it is reporting its type truthfully, the expected payoff or expected utility that they are getting is at least as much as when it is misreporting to some SI. And this inequality should get satisfied for all SI and TI in capital TI. Note that there is no S minus I anymore, because that has already been taken expectation over. And as before, we were going to say that this allocation rule is Bayesian implementable if there exists some payment such that this f comma p is BIC. Note that we are going to call that this mechanism, this f comma p mechanism, to be Bayesian incentive compatible. Of course, implicitly we are assuming that there exists a common prior G, and we are taking the expectation of this allocations and the payments according to that G. So in this setup, we are going to assume the independence of all these priors of this the distribution over these types, and also then we are going to do the characterization of BIC mechanisms, very similar to what we have done for the DSIC mechanisms, and we'll see a very similar result, which is also a result due to Meyerson, but now for the BIC mechanisms. So what we are going to assume is that this the joint distribution of all the types of the agents is decomposable in a product form, and therefore, I mean, this is essentially just saying that all these types are generated independently from each other. Now we are going to use, for simplicity, whenever agent I is reporting its type truthfully, so this Ti is the same as the type that is its true type, that alpha of Ti is the shorthand for that notation instead of writing it twice. So now an allocation rule is going to be non-decreasing in expectation. So remember that earlier we were saying it is non-decreasing, and we were just using the fact that fi of Ti T minus I is at least as much as fi of Si T minus I, and whenever Ti is greater than Si. So we define this as non-decreasingness. Now we are going to apply the expectation with respect to the prior, and we are going to define that it is going to be non-decreasing in expectation if for every Si which is strictly less than Ti, instead of Fi, now the expected allocation is non-decreasing. So that is a non-decreasing in expectation. Quite straightforward definition. We will note that these rules that are non-decreasing that we have defined in the previous case, so all those rules, so all the characterization results that we did and all the examples that we have given earlier, which were non-decreasing, they are always non-decreasing in expectation because they are non-decreasing for every T minus I. So of course, if you take expectation with respect to that, they are also going to be following the non-decreasingness in expectation. But now what can happen is we can possibly have more rules, and we'll see examples of that, more rules that are non-decreasing in expectation, and that opens up many other mechanisms on which we can actually try to maximize our revenue. Okay, so let's first discuss the characterization result, the result which is very similar to the Meyerson's characterization of DSIC mechanism. So here we are trying to do the characterization of the BIC mechanisms. So you're going to say that this mechanism, the result goes as follows. This mechanism f comma p in the independent prior setting, so that is what we are looking at, is BIC if and only if two conditions hold, and those conditions are very much analogous to the DSIC condition. F is non-decreasing in expectation now, and also this payment formula satisfies this integral formula, which is very similar. So your the expected payment at type Ti, again notice that there is no T minus I anymore because they have all been expected over. The expected payment is has three components. First one is the constant component. The second one is alpha Ti times alpha of Ti. So you see Fi has all been replaced with alpha I Ti, and similarly for the last component, which is the integral part. And this should hold for all Ti in capital Ti. So this is the as you can see, is a Bayesian version of the earlier theorem, but the proof can follow in very similar lines. So we will not get into that proof. You can use the ideas of the same proof and just have to take the expectation at appropriate places and redo the proof. I leave that as an exercise. Now, since we said that there are more NDE rules than the ND rules, let us look at one example where it is NDE but not ND. So let's assume that there are two players, and each of them have five possible types. Their type set has five possibilities, and they can be represented in the form of a matrix. So the five different types for player one is given here, and the five possible types are given here. So each of these blocks are actually representing each type profile. And now we can, so this matrix is showing that under which conditions player 1 is getting allocated. So they are represented with 1. The slots that are blank, that the agent 2 is getting allocated the object. Now how can we see that whether alpha 1 t1? So let's look at alpha 1 t1, the expected allocation for player 1 under this t1. You can see when t1 is having this value, then the object is getting allocated to player 2 under all possible circumstances. So if you are actually looking at the corresponding allocation, with probability 1 it is going to player 2, and with probability 0 it is going to go to player 1. So therefore this expected allocation, you can do this calculation, the expected allocation for player 1 when t1 is equal to this value here is going to be 0. Similarly, it is 0 here as well, but here it has a probability of 1 over 5 because there are 5 possibilities. In one of those cases it is getting an allocation, in other 4 cases it is getting allocated to t2. So if you take the expectation over that, it will be 1 by 5. Similarly, if the t1 is this, then it is 2 by 5, and at this value it is 3 by 5. So you can see that as t1 is increasing, because t1 is increasing in this direction, the alpha 1 t1 is also monotonically non-decreasing. Similarly, you can look at the alpha 2 t2. So because here now you'll have to count the number of blank boxes, because we are considering alpha 2, that is allocation probability of player 2. So this will be 3 by 5. In this case it increases, then it goes to 3 by 5 again. Here it is 4 by 5 because there are now 4 blank boxes. Here also it is 4 by 5, and finally it is 1 because it is getting allocated to player 2 altogether. So for both these players they are monotone, but you can already begin to see that it is not monotone for f1 t1 t2 or f2 t1 t2. So you can see that if t2 was having this particular value here, then the allocation, so if we fix t2 at this point, then player 1 is not getting the allocation here, then it is getting the allocation here, but again not getting the allocation here. So this violates the monotonicity condition. So you can also create an example for t2 where it is violating that, but the point is that this is this allocation rule is not non-decreasing. So in the Bayesian setting, we can also define the analog of the individual rationality property. So we are going to say that a mechanism is interim individually rational. So this is something that happens after agent I has observed its own type, but it is still speculating what is the type of the other player. So the expected utility or expected payoff of this agent is always going to be non-negative at that interim level for all types of this player. So if it is deciding whether to participate after watching its own type, it should always participate, because that is the sort of the belief system is telling it. Okay, so now we can actually extend the result of that Bayesian characterization for BIC mechanisms to BIC and IIR mechanism. So you can see that the mechanism F, P is BIC and IIR if and only if the first two conditions are coming directly from the characterization of BIC, and the third condition is telling you that if the constant part in this integral should be non-positive. This is something that we have also seen in the individual rationality condition when we discussed the prior phrase setting. So here this constant is going to be non-positive. So we will not go again to prove this very formally, but we can give the pointers that this conditions 1 and 2 that we have said is coming directly from the BIC mechanism. So this is an if and only if condition, so they are equivalent to BIC. So all that we need to prove is to show that IIR along with this conditions 1 and 2 are equivalent to 3, and that is not very difficult. So in the forward direction, so we want to show that IIR along with 1 and 2 are equivalent to 3. So we first show that if we assume IIR with 1 and 2, this implies 3. So how can we do that? We just need to apply the condition of IIR. So what is IIR? So this one, and we are going to plug the value of Ti to be equal to 0. So therefore this term here vanishes, and all that we have is minus pi I 0 is going to be non-negative, which means this pi I 0 should be non-positive. That is very straightforward. We did the similar exercise in the previous case. Now the other direction, that if we assume condition 3, that is if we assume this is true, and also this 1 and 2, and this inequality is true, so then whether we should have a condition of IIR. So how can we do that? We can just write the utility of player I, and if we now substitute the value of pi I according to that integral formula, what is left? So because this term will get cancelled out, what we will be left with is minus of pi I 0 and this integral part, and we know that this is a probability distribution, so therefore it is going to be non-negative. The integral will be non-negative, and pi I we already know that this is non-positive, so minus of that will be non-negative as well, and that will be greater than or equal to 0. So this is certainly an IIR thing. So alright, so we have actually proved this lemma as well. So we will use these results appropriately when we are trying to find the optimal mechanism which maximizes the revenue.